Today, the part of the lesson that we're going to cover is working with the accuracy. So yesterday's same learning goals as yesterday. We got to be able to be able to determine which measurement is the most accurate. But then we also have to be able to choose an appropriate level of accuracy, which we call our tolerance or our specified tolerance ranges. So what is accuracy? You couldn't answer it while we were correcting, so let's see if you can answer it now with your books open to page 70. What page did I say?
76.
76. Huh. Which book are you going to Okay. What is accuracy? State.
The measurement is the closest of a measured value to the actual or true value.
Okay, so the actual value, the true value, what we want it to be, what it should be, which measurement got closest to it. That's when we're talking about accuracy. So in that one, when we said that the beaker was the more accurate, it was because it was the closest to it. It was nearest to it. So we have to do some subtraction problems basically to figure out which one, the distance away it is from it. Okay, so let's go to page 76, check it out problem. We're going to do check it out problem number 2 there. So we're going to be practicing both precision and accuracy in this one, just like you did in the one in the homework in number 16. So we have a standard mass of 16 ounces is used to test 3 postal scales. The results are shown below. Okay, now first of all, the 16 ounces is what it's like the actual value. It's like it's the one they're testing. They're saying, if the scale is right, it should measure this as 16 ounces. Well, which of the scales, A, B, or C, is the most precise? What do you think? Which of these 3 scales is measuring the most precisely? Go ahead and put something on your notes, which one you think it is, and then give your reason. Which scale is most precise, and then why? Because. So what the scale is measuring, for those of you that are having a little bit difficulty understanding that, the 16-ounce block is purple that is on top of the scale. The measure is given on the green scale. That's the window. The lighter green is the window displaying the weight. It was the measurement. Okay, so which one is most precise? A, B, or C? First of all, are they all measured to the same place value? No. Okay. Well, are they all measured, though, to the same type of measure? Yeah, they're all measured in what? Ounces. Well, as long as they're all measured in ounces, then we don't need to do a conversion problem, do we? They're not measured the same place values, then we think, oh, I might have to do a conversion. But since they're all measured to ounces, don't need to do a conversion. What do we need to do? Yeah, the smallest place value. Which one is taken out the furthest? So which one is it? C, yeah. Scale C is our most precise because it measures to the, what place value is that? To the hundredths. So the word hundred with the THS at the end, because it measures to the hundredths. What did scale A measure to? What did scale A measure to? To the tens place. How about scale B? Tens also. Okay. So C wins the contest, right? Okay, well then which one's the most accurate? Which of those 3 scales is the most accurate? Remember, accuracy means closest to the actual measure. So you think that scale B is? Anybody want to agree with Tate? He says scale B. Okay, what do you think? You're not agreeing with it. What do you think? Maybe we should just go about doing the work and then we can see if we should agree with Tate or not. So here's what we're going to do. We're going to take each of those measures, and if it measures above the actual, then we'll start with that number because it's got a further distance. So what did scale A measure it at? 16.3. Okay, so we're going to say for A, that's more distance than the actual. This way we can avoid using absolute value. Okay, if we take the longer distance, take away the shorter distance, we just need to find out in distance terms how far away that is from the actual. So it is actually how far away?
0.3.
0.3. Okay, so it's 3/10 of an ounce off, right? 3/10 of an ounce off. Okay, how about scale B? What's it measured at? 15.8. Okay, well, that's not the longer distance, is it? 16 is the longer distance. So we're going to take the longer distance and subtract the shorter distance so we have positive distance. That's basically what we're doing, just trying to avoid having to use those absolute value bars because they drive you guys crazy. So how much distance is there this time between these two? 0.2. So this one's only 2/10 of an ounce away. So already it's more accurate, isn't it, than scale A. Okay, scale C. What did it measure it at? 16.07. Well, that's more distance than the actual 16, so we'll take it away that way. So 16 and 7/100 will take away the 16. The longer distance take away the shorter. And how much distance is there on this scale? 0.07. That one's 7/100 of an ounce away. Sometimes the thing to do with decimals is to think of it also as money. So the first one is like 30 cents, right? Second one is 20 cents. The last one is 7 cents, which is the shortest distance. It's 0.07, isn't it? The 7 cents. So is it scale B that's most accurate? No, it actually is scale C. It turns out that scale C also gets the award of being the most accurate. Okay, we're going to say shortest distance. There's our because we showed work. That's how you will support your answers also. Show the distance. Support it and say, you know what, this one has the shortest distance, so I know that makes that one the most accurate. That's where they wanted it to weigh as close to 16 ounces as possible, and that's the one that does. So it is the most accurate. Any questions? Okay, so then let's go talk about tolerance. And so we're going to look at the bottom of the page just below where we were, where it says when you measure a group of objects. So basically what we need to find how much we can tolerate from being what they want it to be. So what level of accuracy do they want to get within, basically? So when you measure a group of objects that are expected to be similar, you may find that there are variations from the expected value. That happens. Tolerance describes the amount by which a measurement is permitted to vary from a specified value. So sometimes, you can't hit it just dead on, but they say, well, give or take, and they'll let you have a little bit of tolerance for it. So tolerance is often expressed as a range of values, such as, you need to look in your books right now. I'm on the last line, almost to the last line of Numbers, page 76. Tolerance is often expressed as a range of values such as 5 millimeters plus or minus 0 3/10 millimeters, which is equivalent to, if you take the 3/10 of a millimeter away, where they're saying they'll tolerate 4 7/10 millimeters. If you add the 3/10, that's what the plus and minus meant. If you add the 3/10 millimeters, it is tolerable up to 5 3/10 millimeters. So just like the baseball problem that you did in the homework for today. So that's one of the ways they express it. But then I also want you to look over on page 77, and I want you to see that they also will express tolerance as a percent. So we're going to work with it both ways. Let's work with it first as tolerance expressed as a percent, okay? So tolerance can be expressed as a percent. So let's look at problem 4A. It looks like we're going to do. So at the very bottom of the page, 4.1, I don't don't know why I didn't write the problem down. So let's write it. 4.1 what is it? What's it measured in? Inches. Plus or minus 5%. That's the one that we're going to express using tolerance expressed as a percent. We're going to show what is that range. You know, 5% really doesn't mean a whole lot to us, but we do know that they'll tolerate. Their tolerance is 5%. So 4.1 times, we have to find out what 5% of 4.1 inches is. So what is 5% as a decimal? 0. Thanks for finishing it for me. Thanks. 0.05. Go ahead, get your calculators out. Let's figure out what 5% of 4 1/10 inches actually is, or we're going to have to approximate, of course. And we're going to round these to the nearest hundredth, okay? So 5% of 4 1/10 inches is approximately what? To the nearest hundredth, what do you get? 0. What? 21? Do you agree with them? Benton doesn't. Okay, what did you get? Okay, so 0 and 21 hundredths, everybody else does agree though? Okay, so 5% of 4 1/10 inches. So we're just saying right here that they're going to allow a tolerance of approximately 21 hundredths of an inch. So basically now what we can say is we can now write the problem like this: 4.1 inches plus or minus 0.21 inches. That's what we're saying. Same thing as we just read on the page prior. It can be 21 hundredths of an inch less. It can be 21 hundredths of an inch more. And right there in the middle should be that 4.1 then. So we need to subtract that from our 4.1. We need to add that to our 4.1. So go ahead and figure out what it is subtracted from it and what it is added to it. And see if you agree with me when you're done. Make sure I'm right. Do we agree? Okay, so basically what we just found now is the low end of the tolerance range and the high end of the tolerance range. So we're going to write it now as a tolerance range: 3 89/100 inches to 4 31/100 inches. This is our final answer. So it was expressed as a percent to start with. We can't just add 5 and subtract 5 because it said 5%, not 5 inches. Seems a little bit unreasonable that they would tolerate 5 inches. If it's 4.1 is the actual, that they would tolerate, ranging from 5 inches below that to 5 inches above. That doesn't even seem reasonable. Now, when you look at your range, what do you suppose you should say to yourself about, do I have a reasonable answer? What would make this a reasonable answer? Without doing any arithmetic, just say, you know what? This seems reasonable because it looks pretty. Eddie?
It's close to the actual.
It's close to the actual. In fact, where should the actual be? In between them, shouldn't it? Yeah. In fact, it should be kind of like smack dab in between them is where it should be. But it should at least fall in between those two numbers. If it doesn't fall in between those two numbers, there's a problem, isn't there? It wouldn't be a reasonable answer. Okay, let's do C. We're going to skip over B and we're going to do C. So let's write down first of all what is our tolerance written as a percent. So it's 85 milligrams plus or minus what percent? What does the book say? How much? So 0.5%, like a half of a percent, is that what it is? Like that? Okay, so this is a half of a percent. So that's not very much, right? Half a percent. So we need to find out what that is, first of all. So don't worry about the plus or minus right now. We need to say, well, we got 85, that we need to know what a 0.5% is. So what is a 0.5%, or this 0.5% changed to its decimal name? What does that look like? You have to divide by 100. Don't make this hard. What did you do in the last problem to get from 5% to 0.05? Or what do we have to do? Move the decimal 2 places to the left. That's the same as dividing by 100. So we do the same thing here. We move this decimal point 2 places to the left. So what would it look like? 0. Point what? 0.005. And we're going to have to round this one also. We'll round to the nearest 100. So what do we get when we take our 85 and multiply it times our 0.5% change to a decimal? Rounded to the nearest 100. What day did I give you guys permission just to come to class without all the supplies? Like calculator? Okay, what is it? Those of you who do come to class prepared. 0.43, okay. So approximately 43 hundredths. And those are milligrams. So really what we have to do now is we're going to find the tolerance range. So we have to take that 85 and we have to subtract it. And what do we get? I get 84.57. You agree with me? Okay, and then we have to do what with it also? That's the low end of the range, and now we have to add it. Well, that should not need a calculator. What's the high end of the range? 85.43. So now we write our tolerance range. You can either say range of tolerance or tolerance range. It does not matter either way. It starts at the low end of 84 and 57 hundredths milligrams to 85 and 43 hundredths milligrams. There's our final answer for this one. They tolerate a 0.5% from the actual, so that means it can be anywhere between these two values of milligrams. Answer seems reasonable because it was a small percent, and 85 falls in between there. Okay. Anybody have any questions about that? Okay, on your papers, would you add, I can see in the next problem, somehow that's the subtraction part of this plus or minus didn't show up, so would you add that in there? Okay, the other thing you're going to be expected to do also is be able to take it from what it can tolerate, what is tolerable, and make that into a percent. So now we're going to work the opposite direction of what we were just doing. Okay? So we need to find out what percent this 1.5 is of 60. It can be, the tolerance of it is a plus or minus 1.5 ounces. What percent is that? That's not going to be just 1.5%. You can't just put a percent sign in place of the ounces. You have to figure out what percent 1.5 is of 60. Does anybody know what we do to make that happen? It's kind of like a quiz grade. You got a 1.5 on this quiz. There's 60 points on it. How would you figure out your grade? I hope you never do this on a quiz, but how would you figure out your grade? You divide. Okay, what would be first? The 1.5 would come first. We would divide, so we take the part, divided by the whole. The whole is 60. And we multiply by what to change it to a percent? 100. Okay. So, the first thing we got to do is figure out what percent 1.5 is of 60. So what percent do we get? Who's your quiz? Pardon? 2.5, oof. That would not be a good quiz score, would it? 2.5%. I just had to use that as an example to help you do percent because that's what you're most used to, is having to figure out a percentage on a grade. So now we're not done. Now it says rewriting specified tolerances as percents. So instead of it being plus or minus the number of ounces, we're going to say plus or minus the percent. So we're going to go back and we're going to say 60 ounces plus or minus. We're going to replace the ounces with that percent that says it can vary by this much, 2.5%, 2.5% less than it, 2.5% more than it. We knew that that 2.5% was 1.5 ounces. What we found was this. So this is our final answer. So when they want to have you rewrite it as a percent, this is what you need to do. Okay? Any questions?